Balancing chemical equations. So this topic asks us to do this. Balance the chemical equation below using the smallest possible whole number stoichiometric coefficients. So we want our stoichiometric coefficients to be whole numbers and to be the simplest whole numbers. So what are stoichiometric coefficients again? Are these the stoichiometric coefficients? No, these are the subscripts. The stoichiometric coefficients are the numbers that go in front of each substance. So if I want to balance this equation, how do I do that? Well, I have to take an invisible line and draw that line straight down the middle. So this will indicate that we're separating the reactants from the products. And to balance an equation means to show that you understand that this reaction is happening in certain proportions. And the balancing an equation should prove that this reaction follows the law of conservation of mass or matter. The number of iron or oxygen atoms on this side of the reaction should equal the number of iron and oxygen atoms on this side of the reaction. So the first step to balancing is to list out the atoms, the kind of atoms that are present. Well, if I look on the left side, I see iron atoms present. If I look also, I see oxygen atoms present. Now, I don't have to look on the right side because, of course, if I have iron and oxygen atoms present on the left, I should have the same kind of atoms present on the right, since this is an alchemy. So iron and oxygen should be present on both sides, and I'm going to put those here down the middle. So the first thing we need to do is do an initial count. How many iron atoms do we have over here? How many over here? So on the left side, we're going to use the skills that we've already worked on, counting atoms in a substance or on sides of a reaction. Let's count the total number of iron atoms on the left side. Well, that will be 2. Let's count the total number of iron atoms on the right side. That will be 1. Let's count the total number of oxygen atoms on the left side. That will be 3. What about on the right side? That would be 2. So looking at this chemical equation as written is not balanced. It violates the law of conservation. Why? Because this says that I started the reaction with 2 iron atoms and ended up with 1. I made an atom disappear. I made matter disappear. This says I started with 3 atoms of oxygen and ended up with 2. So that means that this equation is not balanced and does not happen in these proportions. So we can balance this equation and show that it does follow the law of conservation by changing the coefficients. You never, ever, ever will change the subscripts. By changing the subscripts, you change the chemical, you change the substance. So never balance an equation by adjusting subscripts, only coefficients. So let's see what our coefficients are to start. To start, our coefficients are 1, 1, and 1, because there's nothing there. So that is what we're going to be changing. So what I like to do is just pick the easiest element that can be balanced first. And it looks to me that iron will be the easiest one. How can I balance it? Well, I have 2 iron atoms on this side and 1 on this side. Can I force these 2 numbers to be equal? Yes, I can make this a 2. How can I make that a 2 though? By placing a coefficient of a 2 here. Now, every time you place a new coefficient, you need to stop and recalculate. So if I stop, and if I recalculate now the total number of iron atoms on the right side where I place the coefficient, this is what I should see. So I place the coefficient here, so let's recalculate. I now have 2 iron atoms total on the right side. Subscript times coefficient. 1 times 2 is 2. So now iron seems to be balanced, and the coefficients are now 1, 2, and 1. But oxygen is not yet balanced. What do we see? I have 2 oxygen atoms on this side and 3 on this side. Well, in order to balance this oxygen, what we're going to need is to use what's called a fractional coefficient. Now, this can be balanced without the use of a fractional coefficient, but it'll take a lot of back and forth. The use of fractional coefficients helps us to cut straight to the chase and get the correct coefficient in one go. Furthermore, I really like using fractional coefficients when the unbalanced element is diatomic, as it is in this case. It makes it really, really easy to see and understand how it works and how it solves our problem of having this unbalanced element. Again, because this unbalanced element here is actually a diatomic element. So oxygen is one of the 7 monodiatomic elements. So how does it work? I asked myself, how many oxygen atoms do I have on the other side? I have 3. Here, for this pure oxygen, how many do I need? Well, if I have 3 over here, I need 3 on this side, right? So I place how many oxygen atoms I need total on this side, which is 3. I place it over 2. So if I had 7 oxygen atoms on the left side, then what I'd put over here as the fractional coefficient would be 7 over 2. Well, how does this work conceptually? Well, if I need 3 oxygen atoms over here, and if I put the fractional coefficient as 3/2 over here, what is 3 divided by 2? 3 divided by 2 is 1.5. Well, if I want to calculate total oxygen atoms, what do? Subscript, or atoms times coefficient. If I have 2 oxygen atoms times the coefficient of 1.5, well, what's 1.5 times 2? It's 3, which is exactly the number of oxygen atoms I need to match that side. So now if I recalculate, I have 3/2 times 2 is 3. But there's a problem here. We're supposed to report the smallest possible whole number stoichiometric coefficients. How can I make this 3/2 a whole number? Right now it is a fraction. Well, I can make it a whole number by multiplying all of the coefficients in this chemical equation by the denominator of this fraction. The denominator is 2. So essentially, I'm doubling the coefficients for everything. So what will the new coefficients be? Well, it would look like this. What's 2 times 1? 2. Fe2O3 produces, what's 2 times 2? 4 Fe plus, what is 2 times 3/2? Well, if I take that fraction, let's take 3 over 2 times 2 over 1. That is 6 over 2, which is equal to 3. If you look here, that will cancel with the 2. So it ends up being 3O2. So this is the chemical equation with the correct stoichiometric coefficients to show that this reaction does follow the law of conservation, and it also gives us the proportions in which these substances react with each other, or produced or consumed. So let's again count the number and kind of atoms on each side and see if they are now equal to each other. So on the left and the right, again, I see iron and oxygen atoms. Let's do a count. 2 times 2, 4 iron atoms on the left. 1 times 4, 4 iron atoms on the right. Oxygen, 6 iron atoms on the left. 6 iron atoms on the right. This reaction now as written is now balanced. So what do the coefficients tell me about this reaction? Well, it tells me that if I want to make 4 moles of iron and 3 moles of oxygen, I need 2 moles of Fe2O3. Now, please know that there's not one particular approach, one specific approach that you have to take to balancing chemical equations. I chose to balance the iron atoms first. You could have started with the oxygen atoms. It may have just taken you more steps, and you don't even have to use the fractional coefficient, but it'll take you again more steps and more different math in order to come to the same conclusion.